Hello, everyone. My name is Fiona Gribble. I'm a professor at the University of Cambridge, and we're here today to chat to the winners of the Rising Star Awards. We had a symposium this morning where they presented some of their exciting projects and where they're planning to take their research. So we just got about 5 minutes each to talk to them individually about their projects. And we'll start with Beatriz. Beatriz, can you introduce yourself and just tell us very briefly what your research is about?
My name is Beatriz Merino, and I'm a postdoctoral researcher at the University of Valladolid in the diabetes lab that is led by Irene Cózar and Germán Perdomo. And our focus is the role of insulin-degrading enzyme in health and disease and the relationship with diabetes and insulin resistance.
So this is a enzyme with a strange name because it says that it's an insulin-degrading enzyme, and you told us this morning that it degrades insulin and glucagon and that it does other things. So what do you think is the most exciting parts about this enzyme?
So the reason of this strange name is because the first function that was known was the ability to degrade insulin of this enzyme. But over the last years, more researchers have worked in the area of IDE biology, and it's described that this protein has a multifunctional activity, and the proteolytical activity is one of the main action of this enzyme, but there are another non-proteolytical activity in different tissues that are important also.
And you showed us some very good data that suggests that when IDE isn't there, then your pancreatic islets start behaving very abnormally. Tell us about that.
So when IDE is absent in the pancreatic beta cells, the islet develop a functional immaturity. So when IDE is not there, the secretion of insulin don't respond to glucose, and it's a constitutive insulin secretion. And there is a dysregulation of glucose transporters. There is an overexpression of GLUT1 and subexpression of GLUT2, and all of this phenotype is compatible with a beta cell immaturity. And this is one reason because we think about the role of this enzyme in the development of the endocrine pancreas. So another data that we have in other model is a mouse model with IDE ablation in alpha cells, and in this case the alpha cells with this IDE ablation have a constitutive glucagon secretion, and the islets from these mice are unable to respond correctly to the glucose stimulus, and the proliferation of these cells are dysregulated.
So do you think that IDE, this enzyme, goes wrong in diabetes?
So this is the feeling that we have, because we have different mouse models with specific IDE ablation. We recently published in Metabolism two papers with IDE ablation in the liver, and when you delete this protein, specifically in the hepatocytes, the mouse develops insulin resistance, but without affecting of the insulin clearance, and becomes to the diabetic phenotype. In the same way, when you do a specific ablation in pancreatic beta cells and in pancreatic alpha cells, this mice develops hyperglucagonemia, hyperglycemia, and there are a dysregulation of hormones, of endocrine hormones that speeds up to diabetic phenotype. So I think that when it's absent, there is a problem and probably a risk factor for develop diabetes.
And do you think there's a chance that therapies could be targeted to IDE actually to treat metabolic disease?
Actually, it's proposed that the inhibition of IDE is a good point for the treatment of diabetes, but our data is in the opposite side, and we think that if you inhibit IDE, the speed to the diabetic phenotype is higher, and probably the strategy is not is not this one. So we think that the function of IDE is controversial, and we need to deploy more in the biology of this enzyme, because when it's absent, nothing will in the endocrine pancreas.
So just briefly, so you're going to be studying the function of this enzyme in the islets to work out how how the functional is important for pancreatic islet development.
So the important is in our data points that the importance of this enzyme is in the maturity and the development of the islets. And the aim of this Rising Star project is to deploy in these mechanisms with a model of lineage tracing for evaluate the master regulators in the development of endocrine pancreas.
That's great, Beatriz. Many thanks for talking to us. We'll move on next to Lucille. Lucille, could you introduce yourself, please?
Yeah, my name is Lucile Dollet. I'm a postdoctoral researcher at the Karolinska in Stockholm. I'm working with Professor Julien Zirat and Anna Crook, and our team is mainly focused on type 2 diabetes and skeletal muscle, and also the role of exercise. And I'm personally more interested into the adipose tissue response to exercise and the influence of the circadian rhythm.
So you're moving more into the direction of adipocytes and circadian rhythms in adipocytes. So how important do you think it is that we have a circadian rhythm in our fat stores?
Well, there are several studies that shown that the molecular clock in adipocyte can control lipolysis, but also lipid storage and the secretion of adipokine like adiponectin or leptin. And it seems that this molecular regulation of adipose tissue could influence, for example, the lipid level in plasma. And it seems that the fact that the molecular clock is in several tissue really allowed to synchronize the function of all the peripheral tissue together in the regulation of metabolism.
And do you think it's important when we eat at the time of day, or when we eat relative to exercise? So should we be exercising before or after eating, or does it not matter?
Yeah, that's a good question. So what I was studying is really the effect of the time of the day on the adipose tissue response to exercise. So with mice that were exercising in their rest or active phase. And we see that there is a differential response. But of course, what we also see is that can partly be due to the nutritional status, because when we were fasting the mice, we had similar result that what was happening in the active phase. So probably one part come from the nutritional state, but it seems that not everything in the response come from this. So it can also be a role of the molecular clock. And so basically the rhythm, the circadian rhythm itself, and not only the alternance of feeding, fasting. So that's what we are trying to understand better. And I think that will be something that we really need to decipher to basically understand better when people should exercise to have the maximum beneficial effect. And of course, should they exercise, fasting or feeding, and at what time of the day.
And do you think that the circadian rhythm in your fat stores becomes disturbed in diabetes or metabolic syndrome?
So there were some studies showing that with aging or with insulin resistance, you can have a dampen of the oscillation of the rhythm in the adipose tissue. And there is also evidence from other organs showing that, in people that have obesity or insulin resistance, they have change in this oscillation. And that seems to be really linked with the development of metabolic disease. That's why the idea that external stimulus like feeding or exercise, and we know that they can act on peripheral clock, that could be probably interesting in order to try to either reset the clock or increase the amplitude of the rhythm in tissue. And there were
So do you think there's a chance that if somebody had a disturbed metabolic clock and they started exercising at a particular time of day and eating at defined times of the day, that actually that might improve their rhythm and improve their metabolic state?
So yeah, that's the idea between this whole idea of like chronobiology-based therapy. So there is a recent study that people were exercising in the morning or in the evening, and they show that it was inducing a phase shift of the circadian rhythm in patients. But for that, it was only in healthy adults. And there is more and more study in humans showing that when you control the time of feeding, and actually when you're restricting the time people can eat, and then they have longer fasting time, it can have a beneficial effect on metabolism. And that's why there is a lot of evidence from my study that then can probably affect the rhythm. But of course, we need to confirm this. So, for example, my study was in healthy mice, and now it would be really interesting to look at the effect on high-fat diet-induced insulin-resistant mice, because that would be really relevant for probably moving this towards human.
And then I guess the question is, how important is it that the rhythm is in the fat cells rather than in all the other tissues and organs in our body?
Yeah, of course, it's important in the fat cell. I think it's important in probably all organs, and what we need is really all of them to be synchronized. So what I was looking more is that can we find a time of a day that will increase or maximize the beneficial effect of exercise? And I'm focusing on adipose tissue, but I really think that it's not only adipose tissue related. It's really, change in liver, in skeletal muscle, and having a synchronization of this clock, and also in synchronization in metabolism of this tissue to really allow, like a better metabolic flexibility.
So Lucille, I wish you all the best with your studies. Very well done for winning the award. Pierre, we'll move to you next. I know Pierre. You used to work in our lab. Pierre, could you introduce yourself, please?
Yeah, sure. Thank you, Fiona. So I am Pierre Larraufie. So I'm a research scientist at AgroParisTech in Paris. And I work in the lab of François Blachier, where we study intestinal epithelial cells. And I'm mostly focused on the study of endocrine cells and how metabolism can change their activity.
So Pierre, what do you think are the prospects actually of being able to target endocrine cells as new treatments for diabetes and metabolic disease?
So I think it's quite an interesting question, because we've seen that especially GLP-1 for diabetes treatment can be a good target, and there has been a lot of development of either GLP-1 receptor agonists, dual or tri agonists. But directly targeting the endocrine cells to secrete GLP-1 could be an even better way to do it, because it means it will have a rhythm of GLP-1 secretion, like increased secretion just after a meal, but coming back to basal levels otherwise.
And your particular interest is in how the microbiota interact with the endocrine cells. So tell us, how important do you think that it is for the system to be regulated by our microbiota rather than by our food intake?
So what is quite challenging in reality when we look at where GLP-1 is coming from, it's mostly coming from the distal part of the gut, so in the ileum and the colon, which is where you have most of microbiota being present. And also you have very few nutrients reaching this region, and most of the food which is processed in this part is metabolized by the microbiota. So I think that's the first indication that the microbiota will completely change the environment of the cells. And they will also feed the cells with all these metabolites that can be sensed by endocrine cells and other epithelial cells, making them enabled to react and to also use energy substrate coming from the microbiota. Some studies, when they completely changed microbiota, either using antibiotic treatment or using germ-free mice, showed that the GLP-1 levels, for example, were strongly increased in these mice, so linking between the microbiota and the GLP-1 production and secretion.
So what's your hope? Is it that we'll actually be able to manipulate the microbiota and therefore improve the endocrine cell function? Is that a realistic prospect?
So I think that's a bit a long-term goal, but it's something many people also manage to achieve using either prebiotics or probiotics, where they can find specific strains or specific food compounds that have beneficial impacts. However, often the mechanisms linking the beneficial impacts and the specific strain of probiotics are not known. What I'm going to do is really to try to understand which molecules, which bacterial metabolites are important to regulate endocrine cell functions, and mostly how can they change their metabolism and their energy metabolism, and to know if it matters or not to change GLP-1 secretion in the cells.
So you're going to do that in cell models. Is that your starting point?
Yeah, so we will start using in vitro models, because in that case we have a much more regulated environment and it's easier to control what cells use as an energy substrate or everything, whereas the environment in the gut is way too complex to study directly. However, we hope that if we manage to find interesting compounds or upregulation of, for example, specific pathways in microbiota, then we might be able to modulate the microbiota directly and see in vivo, first in mice, what's happening.
Very good, Pierre. I wish you all the best with your studies. I hope they go well. And next we'll move on to Alexandra. Could you introduce yourself to everyone, please?
Yes, so my name is Alexandra Smink. I'm a postdoctoral fellow in the medical biology department of the UMCG, which is in Groningen in the Netherlands. And my work focuses on the development of an artificial islet transplantation site for the treatment of type 1 diabetes.
So tell us a bit more about this device and what it could be used for, because you're working with donor islets at the moment, but how widely could it be used for implanting islet cells?
Yeah, so at the moment we are working with donor islets because we don't have the expertise in our lab for we don't have insulin producing cells from stem cells, for example. But to overcome the donor shortage problem, it's definitely something in the future I would like to test as well, to test my artificial transplantation site together with insulin producing cells derived from stem cells. And I think it's even more important for these type of cells to have such an artificial transplantation site, because you can really contain these cells in an enclosed space, so it prevents these cells from wandering throughout the whole body and maybe doing things they should not do. So I think this is definitely also beneficial for the insulin producing stem cells.
You're not the it's the holy grail really to be able to develop devices that could be used for islet transplantation. So how is your approach different from what other people are doing? Why are you going to succeed, do you think, when other people, or why are you going to be at the head of the field with this?
Yeah, so one thing that is, I think, rather unique on our approach is that we implant our device before we transplant islets. So this pre-vascularization phase, as we call it, we use to attract a lot of blood vessels towards the device. So creating already this highly vascularized and great environment before you introduce the islets, and also in this way you allow the immune response that's almost always there. There's almost some kind of an immune response if you place a material in the human body that can dampen, and then this could influence islets or insulin-producing cells if they are already there. So there we implant first without the cells, and then after a few weeks, when we have this nice environment for islets, then we transplant the islets in.
And what do you think is going to be the hardest part to optimize?
Well, so thinking about translating towards a clinic, the first thing that needs to be done, of course, is scaling up the device. So now it's the size of an SD card for mice and rat studies, but if we have to go to the clinic, then of course you need more, something like a credit card size device, and then the vascularization becomes even more important, because you can imagine that the core of that device, it takes longer, or it needs a different approach to get it whole vascularized before it's ready for islet transplantation. And then, as I already shortly mentioned, like the donor shortage might be a problem for translating to clinic, where there you can maybe use insulin-producing stem cells. And another thing is the protecting against rejection. You need to find this nice balance between having a highly vascularized pocket, but also protecting the islets from the immune system. To be able to make this step to the clinic, I think.
So your approach is to bring the vasculature as close up to the islet as it can, but without allowing it to penetrate the islet, because then the immune cells will get in. Is that right?
Yeah. So for this Rising Star proposal, I aim to encapsulate the islets in an immuno-isolating membrane, and then it's of course important that the diffusion distance to the vasculature is not too large, because then the islets cannot function very well. So we want to create a highly vascularized pocket, and then make a little membrane around each islet to protect them against the immune system. But another option could be, for example, creating local immunity protection within the whole scaffold, so that you don't encapsulate each islet, so that they can just interact with the vasculature much easier, but then that you don't have to give systemic immunosuppression, but only locally, for example.
And final question, do you think there will be any issues with the timing of how long it'll take for glucose to diffuse into the islets and for insulin to diffuse out, since they need to get past this barrier that'll protect them from the immune system?
Yes, the risk, of course, if you encapsulate islets, is that the diffusion distance is larger, and it's of course already larger than if you look at the diffusion distance, for example, in the native pancreas. So I think we should take the native pancreas environment as an example for how we should create our artificial transplantation site. The timing that is used normally in a normal healthy human being, that should be something we should try to achieve, or at least mimic as close as possible, to get the best out of this treatment for type 1 diabetes, I think.
So very exciting, Alexandra. It'd be fantastic if you can make that work. And I'd like to thank all of you for chatting to me after the symposium. And I say, wish you all the very best. Congratulations for having won the award. And we wish you all the best in your future. We look forward to seeing you back at future ESD meetings to tell us how you've progressed with your research. So thank you very much.